Okay, today we'll continue with compensated semiconductors. But before that, let's recap on what we have discussed yesterday on degenerate semiconductors. So what is degenerate semiconductor? How do you define a degenerate semiconductor? Anyone? Let's warm up a bit. Alia. Faris, high doping level. Okay. One keyword, high doping level. Alia Nasrin. Kavina, act like a metal due to high doping level. All right. Okay. What else? Semiconductor with high doping level that starts to act like a metal. All right. What else? Anything else that you can say about a degenerate semiconductor? How about examples of degenerate semiconductors? Any examples? Zinc oxide, okay. Anything else? ITO, yep. Hazik, you're working on zinc oxide, right? Oh no, somebody else. Who works on zinc oxide? EF will go above EC or below EV. Yep, that's good. If doping is high enough, then the energy states, the Fermi level of the EF of the degenerate semiconductor will even go beyond EC or EV. All right, you try zinc oxide on wafer. Okay. So any particular purpose? Zinc oxide on wafer. Okay. For what? What are you trying to get actually? Increase light absorption in the silicon, is it? In the wafer? Okay. All right. Anybody else trying on the oxide? Who else working on the oxide? How about siapa yang tak pernah panggil lagi ni? Nur Ahadiah. Jarang dengar Ahadiah. So, what else about degenerate semiconductor? Oh, Sri Izyani. Any other important properties of degenerate semiconductors that we haven't mentioned? Ada lagi ke? What else we haven't discussed? We haven't mentioned? Yeah, transparent. Yes, transparent. Okay. Okay, those are the key things. Okay, those are among the key things you have mentioned just now. Right. So let's move on to another type of another group of semiconductors. We call it compensated semiconductors. So what is compensated semiconductor? It is a type of a group of semiconductor which contains both donor and acceptor impurity atoms in the same region. So So we'll see later on, you can actually dope the semiconductor with both dopant types to be able to generate equal amount of carriers in the semiconductor. Okay, how do we do that? By diffusing impurity acceptor atoms into an n-type material, or by diffusing donor impurities into a p-type material. Okay, so the process that we do is called diffusion process. So we're going to learn later on in this, not in this course though, the details. In 487, the process name is called diffusion. So it's a process of incorporating the dopant atoms into the silicon lattice. So whatever your dopant atoms are, so in this case, if you want to achieve compensated semiconductor, you need to diffuse opposite impurity into your semiconductor material. For example, if you have an n-type, material, what is the majority carrier in n-type? Anyone? Electron, right? So majority carrier in n-type is electron. So in order for you to achieve compensated semiconductor, so you want to compensate the number of carriers, so you are actually canceling out more or less effectively. So you need to incorporate opposite dopant atoms. Okay, so in this case, you need to incorporate acceptor atoms, which will introduce more holes into the lattice, right? So you are introducing Na, or you are introducing holes, more and more holes, because you know that your majority carriers in the n-type is electrons, so you want to cancel out more or less. So you are actually compensating the semiconductor material. Or on the other hand, you can also diffuse donor atoms like electrons, which contains electrons, into p-type, which contains holes as the majority carriers. So again, opposite type of carriers. Okay. An n-type semiconductor, compensated semiconductor, occurs when Nd is more than Na. Okay, Nd is more than Na, and a p-type compensated semiconductor occurs when your Na is more than Nd. So you're actually canceling out. So you need to break the threshold in order for you to get compensated semiconductors. If Na is equals to N, if Na is equals to equal to Nd, if Na is equal to Nd, then we call it as completely compensated semiconductor. Characteristics of an intrinsic material. So what happens when you have Na equals to Nd? What's your effective majority carriers in the silicon? So at this point, what is your effective majority carriers in your silicon? Anyone? Apa maksudnya? When Na is equal to Nd? Na equals to Nd. So what does it mean? When A is equal to B, then what does it mean? Electrons and holes are the same, right? So if you have the same number of electrons and holes, do you have any majority carriers? No, right? What happens if you bring Nd to one side? Na minus Nd will be equal to, simple math, kosong kan? Because Na is equal to Nd. So there's no effective majority carriers because you are canceling out the majority carriers in the semiconductor material. So you started with a majority carrier because you either started with a p-type or with an n-type. So with either holes as majority in p-type or electrons as majority in n-type. But the moment you compensate, you adding on opposite dopant atoms, so opposite charges more or less when they are ionized, so they will cancel out the effective majority carriers, leaving the final value to 0. Okay, when your Na is completely equal to Nd, or your semiconductor is now completely compensated. Compensated semiconductors are created quite naturally during device fabrication, as we'll see later on. So for example, if you want to dope a semiconductor material, so you start with an n-type silicon, for example, and you want to dope your top layer in the wafer, for example, to make it p-type. So say if you run the project for your FYP with n-type silicon, then in order to form a p-n junction, you need to diffuse. So that's the word diffuse, by diffusion process, a very thin layer on top of your silicon with a p-type to make it as p-type silicon, so that you're gonna have a p-n junction eventually, p here and n, right? P sits on n. So to be able to do that, you need to go through this process. Okay, is it easier to compensate a semiconductor, or is it easier to dope a semiconductor from intrinsic? So if you are given two types of wafers, one is n-type silicon, one is intrinsic silicon, is it easier to dope p-type to the intrinsic or to the n-type silicon? So if you're going to get p-type eventually on the top surface, is it easier to get it on a top surface of an intrinsic or on an n-type? You want to form a p-type now. Which one is easier? Okay, Amiro said intrinsic. Okay, Shreya said n-type. Logically, which one is easier? Do you want to start from one polarity or something neutral? Logically, yeah. Say if I draw a spectrum here, for example, okay, this is intrinsic in the middle, intrinsic kat tengah. So if you go to the left, you are n-type. If you go to the right, you are p-type. Just imagine as a spectrum, okay? So intrinsic is here, right here in the middle, 10 to the 10. So you start off with here, n-type wafer. Option number 1. Option number 2 is you start here, intrinsic. You want to achieve p-type. Which one is easier? Neutral, right? You start off intrinsic, it's undoped. Logically, it's easier to achieve in undoped compared to compensate your semiconductor. But it's not that difficult, though, to compensate, because this is what we do normally. You start off with a p-type silicon, then you want to form a p-n junction. What you do is just diffuse an n-type layer on top of your p-type silicon, and it happens quite easy as well. It's not that difficult. All right, variation of EF with doping. We have discussed this one briefly in the last few sessions, right? So just imagine if you have an intrinsic silicon on the left of the spectrum. So you start off somewhere here on the left, where your so what's the carrier density for your intrinsic? If you have undoped, so what is the carrier density inside the silicon? On the left. Berapa? Go ahead.
1 times 10 to the power of 10.
Yep, 1 times 10 to the power of 10, right? So it's slightly to the left, slightly more to the left of this figure. So you're going to start like somewhere here, perhaps. if you extrapolate this line, okay, somewhere there, Ni equals to 10 to the 10 per centimeter cube for silicon, yeah, for silicon, remember. So if you dope your silicon to n-type or p-type, is going to move accordingly. So note that when you have your intrinsic, your EF is equals to your mid gap, right? Eg over 2, Eg over 2, which is EC minus EV over 2. So the space between EC and EV divided by 2. So you're going to get your EF intrinsic, right? That's how it started, EF intrinsic. So say if you want to dope your silicon to n-type, so you're going to add more phosphorus or more arsenic or more antimony. And at the same time, when you keep increasing the doping level, your EF is going to increase as well. We discussed this one last time. So it's going to go up into closer to EC as you increase the doping level for your n-type. So the same is also true for p-type, where when you increase the doping level for p-type by adding more gallium or boron, so your EF is going to change as well. It's going to change closer and closer and closer to the valence band. Okay, so that's the change of position of Fermi level as a function of doping for both p-type and n-type. So as doping levels increase, the Fermi level moves closer to CB for n-type and closer to VB for the p-type. Okay, quite straightforward. So what happens at this point, for example, say at this point on the far right, so that's like 10 to the 18. So if you go beyond that, if you keep increasing the doping level, what's going to happen to the EF at this point? So you are now at 10 to the 18 here. Then you keep increasing the doping level. What happens to the EF? Apa jadi? It's going to go. What's going to happen to the EF? We just learned yesterday, right? It's going to go beyond, right? Beyond EC or beyond EV, depending on the polarity, okay? If you're talking about n-type, that's going to go beyond EC. And at this point, the silicon has become, what do you call that now? It has become that, even before 3 kT, after the 3 kT away. So what do we call that now? Conductor. It has become conductor already. Degenerate, right? Degenerate semiconductor. So it has now become a degenerate semiconductor since the EF is less than 3 kT away from either band edge. Okay. So if the value is less than 3 kT away, it has started to become a degenerate semiconductor. And if you keep increasing the doping level of the n-type silicon, for example, or p-type silicon, then your EF is going to go into conduction band or valence band. All right. So next, what's going to happen to the EF with temperature? So let's say, so the EF minus EF intrinsic for your y-axis and temperature for the x-axis. So the intrinsic carrier concentration Ni is a strong function of temperature. So EF is a function of temperature as well. Okay, so EF is a function of temperature because your Ni is also a function of temperature. So you can also say that your Ni is also a function of EF. Okay, because both depend on temperature to begin with. So as the temperature increases, if you see on the x-axis, if you go to the right, increasing the temperature from 0 Kelvin, 0 Kelvin to the 600 Kelvin on the right, far right. Ni increases, so intrinsic carrier density increases, okay? Intrinsic carrier density increases as temperature increases, and as a result, the EF move closer to the intrinsic Fermi level, okay? Say if you start with, for example, if you pick p-type, for example, if you pick p-type, so let's look at p-type. So look at the curve related to p-type, close to p-type. So when you increase your temperature, increase, that means you're going to the right of the curve of the graph, going say from 0 Kelvin up to 600 Kelvin, your Ni is going to increase, and as a result, your EF is going to move closer to the intrinsic Fermi level. So intrinsic Fermi level, where is it? Where's the location of intrinsic Fermi level? On the y-axis, where is it? Yeah, 0, right? Yep, 0. So intrinsic Fermi level. So what does it mean by 0 there? Why is it 0? That means when your y-axis is 0 or in the middle, so that means your EF minus EF intrinsic is the same thing, right? Okay, when your EF, when your Fermi level of your silicon is equal to intrinsic Fermi level, so that means your E minus EF will be equal to 0, right? Because now on the y-axis we are plotting EF minus EF intrinsic. So that means EF is equal to EF intrinsic. Or your semiconductor material, even though you start off with p-type, if you increase your temperature, high enough, your EF will actually move towards intrinsic. Okay, why is it so? Let's have a look. So the details here, Ni increases when your temperature increases, your Ni increases in your p-type or in your n-type. Kalau p-type, then it's going to move up to 0. If you start with an n-type, it's going to move down to 0, heading to the center, right? So as a result, your EF move closer to the intrinsic Fermi level where you get this. At high temperature, material begins to lose its extrinsic characteristics. So remember, you start off with extrinsic, either p-type or n-type, which is extrinsic, right? You dope your silicon. But if you increase your temperature high enough, your material, your silicon, for example, in this case, begins to lose its characteristic, its extrinsic characteristics at high temperature. So remember, you start off with extrinsic, but if your temperature is high enough, it's going to lose the extrinsic properties, and it begins to behave more like an intrinsic semiconductor. So if you have your extrinsic at the beginning, if you increase the temperature high enough, your semiconductor is going to be intrinsic eventually. Okay, eventually it's going to be intrinsic. So at very low temperature, freeze out occurs. At very low temperature, 0 Kelvin, freeze out occurs. The Boltzmann approximation is no longer valid, and the equation we derive for the Fermi level position no longer apply at freeze out condition. Okay, so the key here is when you increase your temperature, your semiconductor material is going to lose its extrinsic properties, because now it's going to behave like an intrinsic semiconductor. So then how do we freeze carriers? Can we freeze carriers? Have you ever tried to freeze carriers? Have you done any low temperature experiment? Below room temperature, have you tried any? Anyone? Or your FYP is on low temperature region? Tak ada. No one. All room temperature or high temperature. Okay, doesn't matter. All right, so what's happening is you can see on this graph, figure 25. So the y-axis shows electron density, okay, electron density on the y-axis, and your x-axis shows temperature, right, from 0 to 600 Kelvin. So donor concentration in this case is 1015. Sorry, the donor is 1015. So now is the silicon p-type or n-type. So now your starting material is n-type or p-type. Your donor is 1015. Donor level is 10 to the 15 per centimeter cube. Are you having p-type or n-type silicon? Anyone? P-type or n-type? Donor. What is donor? N-type, right? Donor donates electrons, extra electrons. Extra electrons means more n-type, negatively charged, right? If we're talking about Na acceptor, then p-type, right? So this one donor always n-type. So jangan confuse, don't be confused, because I always get this, ND, but some students write p-type. And the moment you write p-type, then your interpretation could be wrong in the next steps as well, in the following steps. Okay, so get it right first. ND is equals to 10 to the 15. So now we're trying to increase the temperature of our n-type silicon. Okay, n-type silicon. N-type, So at low temperatures, the thermal energy in the crystal is not sufficient to ionize all the donor impurities present. Remember last time we discussed that you may incorporate dopants into the lattice, but if they are not ionized, no point, right? They're just sitting there doing nothing, not improving the electrical conductivity of your silicon. Because the goal is to alter the conductivity, to improve, for example. But if they are there doing nothing, then they are not changing anything on the electrical properties of the silicon. Therefore, they need to be ionized. But at low temperatures, thermal energy is not sufficient to ionize the dopants. Recall last time we discussed about the energy needed in order to ionize is about 002 eV. So that means the temperature is not even enough. It's not even surpassing 002 electron volt in order to ionize. So as a result, some electrons are frozen. In fact, most electrons are frozen at the donor level. So they are there at the donor level, and the electron density is less than the donor concentration. So they are there at the donor level. That means if you want to translate this in the form of Venn diagram, kat mana donor level? Where's the donor level? Near to EC or near to EV? EC, right? So donor level will be here, and D, if you like. But they are just there. They're not ionized, right? They're not ionized. So therefore, as a result, the electron density, the resulting electron density, will be less than the donor concentration. Remember last time, what did we assume? We assume that N is approximately equal to what? Not question mark. We assume that when you include donor, when you incorporate donor atoms into the lattice, yeah, we assume that N is approximately equal than ND, right? And we assume that because we assume 100% of ionization. So all dopants are ionized, all, okay, all. So in this case, when the temperature is low, it is too low, so we don't have ionization, we don't have enough ionization. As a result, N is way lower than the ND, which is the intended value, right? The intended value of N will be Nd, but due to the low temperature of the silicon at that particular time, Na will be way lower than Nd. As the temperature is increased, so this is explaining the graph, okay? When you go from the left to the right. So tadi kita discuss kat sini. This one. Done. Now, as the temperature is increased, going to the right slowly, the condition of complete ionization is reached. So we can now safely assume that 100% of the donors or donor atoms are ionized. Therefore, the goal is achieved, and the goal is to get N approximately equal to Nd. So now we can assume complete ionization. Okay, say you are here at room temperature, maybe. We're going to see later on, don't worry yet. So that's what's happening. As the temperature is further increased, so we're going further and further to the right. So the electron concentration remains essentially the same over a wide temperature region, which is here. So we are ionizing more and more of the dopants that we have incorporated into the lattice. So it remains in the extrinsic region, which is the flat region there, right? So the first region here just now on the left is called freeze-out region due to the low temperature. And in the second region, we are now in extrinsic region as intended, because we started off with N-type silicon, and now we managed to ionize more and more of the dopants as the temperature is increased. So we're now in extrinsic region. However, as the temperature is increased even further, so we're now getting into region number 3. Sorry. So we're now getting to region number 3. As the temperature is increased further, we reach a point where the intrinsic carrier concentration becomes comparable to the donor concentration. So at this point, Ni will be high enough and will be close to the value of Nd. So say if your Nd is 1015, at this point your Ni will also be close to 1015. Okay, so in this case we started off with 1015, right? So that means at this point, when you start to enter the region number 3, your Ni will be close to the value of Nd, and beyond this point, the semiconductor becomes intrinsic. So this is region number 3, where your semiconductor loses its extrinsic properties. So at this point, it loses its extrinsic properties. Then it gets into region number 3, where your electron density will be dominated by Ni rather than Nd. Okay? So region number 3, your electron density will be dominated by Ni rather than Nd because of this. This portion. So when the thermally generated, so at this point, when you increase your temperature too high, you're going to have, this region number 3, you're going to have a lot of thermal excitation. So thermal excitation due to the high temperature, say at 600 Kelvin. So this is going to supply the KT to the electrons, right? Boltzmann constant time the current temperature. So they'll give you a lot of thermal excitation, and as a result, the electrons excited into the conduction band is dominated by thermal excitation rather than the contribution by the donor atoms, right? Donor atoms. So Ni is going to dominate Nd. So beyond this point, the semiconductor becomes intrinsic, so no longer extrinsic. So region number 1 is freeze-out region. Region number 2 is the extrinsic region. So you can say that you can see the flat region there between 100 plus to close to 500. But when the Ni is more than, when Ni starts to be close to Nd, you're going to go into region number 3. where the semiconductor is going to lose its extrinsic properties and becomes intrinsic again. Okay, so one way to convert your extrinsic silicon to intrinsic is by heating up the silicon. So you don't have to, well, we learned about compensated semiconductor, right? Where your Na is equal to Nd and you don't have any effective majority carriers, which is intrinsic, isn't it? So you can either compensate to cancel out the effective majority carriers, or you can also maintain the N-type silicon and heat up the silicon high enough so that the Ni will be dominant over Nd, and your electron density will be dominated by thermal excitation. So that's another way to turn your extrinsic silicon into intrinsic silicon. So one is by cancellation of dopant, and second is by heating up the silicon, right? So two ways. Now you know how to convert your extrinsic to intrinsic. So intrinsic to extrinsic, on the other hand, is very straightforward. You just add on the dopants, right? To make it more N-type or more P-type. So the temperature at which the semiconductor becomes intrinsic depends on the purity concentration and the band gap value. So it depends on what's your starting value. Okay, if you're starting at 1015, it's different. 1016 is going to be different. 1017 is going to be different. And it also depends on the band gap of your semiconductor material. Either it's 1.1, 1.4, 0.7. So that the temperature at which the semiconductor becomes intrinsic will be different depending on these two factors, impurity concentration and also the band gap. Right? Done. So let's get to the calculation. So was it clear just now on the transition of your phase out to extrinsic to intrinsic? Okay, is it clear what's happening? So by manipulating the temperature, you can actually change the properties of your extrinsic semiconductor material. Right, so let's get to question number 1, and I'll leave you with number 2 and number 3. Senang je ni kan? Have you tried? Have you seen the solution? How to solve this problem? All right, calculation. Let's go to number 1. You are given with this band diagram, band structure. So your EC, EF, and EV are given. So your EC to EV is 1.12. So what is this semiconductor material? EC to EV is 1.12 electron volt. So what is this semiconductor material? Silicon, right? Because EC to EV is your EG, it's your band gap, right? It's the forbidden gap. So the space between is the EG. So therefore, since it's 1.12, so that means it's crystalline silicon. To be more accurate, it's crystalline silicon rather than just silicon, right? Because silicon can also be amorphous, and amorphous has 1.8 EV, which is different. So, well, generally, it's okay to say silicon, but to be more accurate, it's crystalline silicon, because we also have amorphous silicon, which has different band gap. All right, so EF minus EV, so distance between Fermi level to EV is 0.8 electron volts. Question number 1. Now, question is here. I read the answer right away. Okay, sorry, let me just recap the question. So the band structure of a silicon sample is Ni, is given. So Ni is 1 times 10 to the 10. So the sample is at room temperature, 200 Kelvin. Answer the following questions. Note that the density of states in the conduction band is given and density of states in the valence band is given. Question number 1. What is the doping type of the material? Why is it so? P-type or N-type? Simple one. P-type or N-type? N-type. So why is it N-type? Kenapa N-type? Kalau tengok sekali dah tahu kan? Why is it N-type? Because EF is near to EC. You can also say that your EF is higher than the mid gap. Okay, so it's moving towards N-type. Moving towards N-type. This one is very straightforward because it's very close. A non-straightforward one would be EF is not that close, but higher than mid gap, right? So it's N-type because your EF is higher than mid gap or close to EC is fine. What is the dopant density, right? So EF is part number 1 is clear, higher than mid gap, more than 0.56 EV. Question number 2, what is the dopant density? So you can use this equation, n equals to nc exponential ef minus ec over kt. So you've got everything already. So you know the nc, density of states in the conduction band. You can plug in the temperature there, it's given as well. And then your ef is known, right? Ef minus ec is known. Okay, then your KT is also known, your constant times the temperature. Then you're going to get 1.4 times 10 to the 14 per centimeter cube, right? So if the question asks, is the semiconductor material lightly doped or heavily doped? What is your answer? Is your silicon lightly doped or heavily doped or moderately doped? Lightly doped, yeah, because it's 10 to the 14, right? Right, straightforward. Part number 3. What is the minority carrier concentration in the sample at thermal equilibrium? Minority carrier, how do we do that? How do we calculate minority carrier? So what is the majority carrier now in this silicon? Electron, and the value of the majority carrier concentration is 1.4 times 10 to the 14 per centimeter cube of electrons as the majority carrier in your silicon now. So therefore, to be able to calculate your minority carrier, you just use the law of mass action, n times p equals to ni squared. Therefore, p will be equal to, why you calculate? Can you not calculate? Do you know the value if you don't calculate?
Dia doktor, tapi soalan dia minta what saja. Dia tanya apa je kan, kenapa?
Yeah. What is the minority carrier concentration in the sample at thermal? Oh, okay. You mean will just saying whole will be enough?
Kenapa?
Okay. I got you. Okay, right. So because the previous question asked what is the dopant density. So it's somehow related to the previous question. So the moment you are asked to give the dopant density, so it means the next one would be close, usually, right? So the safest bet would be to state the minority carrier type and also state the value. Okay. So you can also, well, the question can be like, what is the level of dopant concentration? Can be, but typically if your previous question asked the value, then the next question would also ask for the value, right? So what's the minority carrier concentration? In this case, you can also say it's p-type and the value is given by n times p equals to ni squared. Therefore, p will be equals to ni squared over n. So you can also use ni as 1.5 or you can also use 1.0. Either one is fine. If you want to do the calculation easily, then just use 1. So you don't have to square the 1.5. And the process will be a lot easier to do. So if you give either one, they will be considered correct. Okay, 1.5 is okay, 1.0 is okay, but to be easy, just use 1.0. So 1.0, for example, times 10 to the 10 squared over 1.4 times 10 to the 14, and your minority carrier concentration will therefore be 1.6 times 10 to the 6 per centimeter cube of whole concentration. Okay, whole. So please check. Please check and make sure you are okay. 1.5. I think question give 1.0. Yeah, correct, Faris. You can use either one. If okay, well, the ground rules like this. If it's not stating anything, then you can use anything. If it's stated, then use that one. But normally I'm open to either one, right? Normally the questions will normally be form of open for your choice. But for the sake of easy calculation, then use 1.0. So then if you use 1.0, then your value will be, so let's see, can you try calculate if you use 1.0? What's your answer? What do you get? Okay, kira dulu. Anyone? Did you get it, Faris? So 0.7 times 10 to the 6. Okay, 0.7 times 10 to the 6. Or 7 times 10 to the 5, is it? 7 times, oh no? Betul? Okay, so as long as you can show the answer by using the correct calculation, is okay. Faris dia ni tu apa? Belum lunch ke Faris? Saya belum lunch ni. All right. So I leave you with calculation number 2 and 3. Yeah. Example number 2 and 3 is given already. So you can use, for example, number 2. You can use the density of states, NC, N0, NV. Okay, same thing. So my tip for this sort of question, if you're given, when you're given the information, please first draw the band diagram, the band structure. Draw the EC, the EF, the EV, the EI, the EG. The moment you've drawn the diagram, it will become clearer. Okay, comparing to if you just know the value state, EF is what equals, so it's just, you don't draw yet, then it's going to be, you can get wrong more easily compared to if you draw your band structure, because the moment you see, then it's going to be a lot clearer. Yeah, because some question here like EC minus EF, so you need to see the difference between your band edge and your Fermi level, and then EF minus EV. So the moment you've drawn and you've got the value for the section number 1, for example, then you can label the answer on the diagram, and straight away you can tell if your EG is this much, if this one is this much, then therefore the balance is this much, right? So be graphical, draw and label. The moment you get the answer, just put on the graph or put on the band structure, and sometimes you don't even have to calculate, you can tell already straight away from the band structure, right? So EF minus EFI and stuff like that. So the same goes to question number 3 as well. So the position of Fermi level with respect to the valence band. So EF against EV, okay? EF against EV. So your EF will always be higher than EV unless you have a degenerate p-type where your EF is below EV, okay? Else, your EF will always be above EV, either it's closer or not too close with the EV, right? Depending on the doping level. All right, then I'll leave you with that. Go back and try number 2 and number 3 for yourself. The foundations are the same. Any questions?
No, Doctor.
151. Tada. All good so far? Can you follow from day 1 until now?
So far, so good, Doctor.
So far, so good. Hungry already?
Yeah, I want to go lunch.
Me too. Let's go lunch. Separately.
Let's go, Doctor.
Okay, so in our tomorrow, Thursday, right? Thursday, 10 a.m. So tomorrow, we're going to continue with carrier transport phenomena. So we're going to learn about drift. We're going to learn about diffusion of carriers. How do the carriers move around? When you have electric field, we don't have electric field, because this is going to lead into formation of p-n junction. And then how does the carrier move? Okay, bye-bye. See ya. Assalamualaikum. Take care.
Thank you, Doctor.
Thank you. Bye.